Earlier, we came up with a plan to use a simulation to test for an association, and if we want, we can carry that out with an applet. So I'm going to the multiple proportions applet here since we have more than two groups. So I'm going to start by putting in my data. I don't have to enter it like this with one row for every person. I can enter it in as a table, so that's faster. That's what I'm going to do. So I start by clicking clear. And then I'm going to do headings for my three groups. So I had real, sham, and non, and I'm just putting spaces between these. And then substantial reduction in pain, I want just one word for that, so I'm just going to say better. And then put in the counts. So in the real group, it was 184, in the sham, 171, and in the non, 106. And then for those that didn't have substantial improvement, I'm just going to say not. And the counts were 203, 216, and 282. So this was actually a typo in the first video. Sorry about that. I said 232. It should be 282. And then I'm going to click Use Table. And now I can tell from the segmented bar graph that this is about right, that I've got real and sham sort of similar to each other, and then a lower proportion that improved in the non-acupuncture therapy group. You do get to pick your statistic that you want to use to summarize this. And we're going to use the chi-squared statistic. So this calculates for us the chi-squared statistic we did earlier, 38.054. If I want to do the simulation itself, it doesn't show us the cards here, but basically it's doing just the responses. So we've got 461 of one color to represent the people who improved, 701 to represent those who didn't improve, and we're not labeling them by treatment group or anything because we're assuming that all the treatments are equally effective, that we're just putting them all together and shuffling them. So I'm going to click shuffle. Let's look at it in the plot. That's probably a little more interesting. So this came out pretty even, and so the chi-square statistic is going to be pretty small here, right? Because the observed and the expected would be similar in the case where there's very little association in the sample. So we've got our chi-square statistic there. And if I do other ones, I'm going to get slightly different outcomes and different chi-squares. So you may notice that these are coming out pretty close to even just about every time. And that's actually not that surprising because we have pretty large sample sizes, right? Over 300 in each group. And so, that's enough, that's a big enough sample size that we would expect things to pretty much balance out. So let's go ahead and use a much larger sample size to see what range of chi-square statistics would occur just by chance. So to get up to 10,000, I'm going to do 9,990. And that's giving me my distribution of chi-square statistics. I can see really without even counting it, but I'll put it in here just to show you that virtually never are you going to get chi-square statistics as large as what we got in our sample. So a chi-square statistic of 38 would be extremely unlikely to occur just by chance. So here we've used a simulation to figure out what our null distribution is. It gives us a point of comparison for our statistic, and use that to decide that we have strong evidence. But if you didn't want to do the simulation, you could also use a theory-based approach, assuming that certain conditions are met. So if I click Overlay chi-squared distribution, you can see that this pretty much goes along with the values that we got when we just shuffled and dealt. So this is giving us a theoretical model for our null distribution. So a nice thing about the chi-square statistic is that it can be predicted by a theoretical model, assuming that validity conditions are met. So instead of carrying out a simulation, we can use a chi-square distribution with certain degrees of freedom. So remember, there's different versions of the chi-square distribution depending on your degrees of freedom. And here the degrees of freedom depends on the size of the table. So when it says R-1, R here is going to be our number of rows. And then C-1, C is the number of columns. And when we count the rows and the columns, we don't include the totals. So basically you're just thinking about how many levels each variable has. So to calculate this for the acupuncture example, we had 2 rows because our outcomes were just substantial reduction in pain or no substantial reduction. So we've got 2 rows, 2 minus 1. And we had 3 columns because we had 3 treatment groups, so 3 minus 1. And we end up with 2 degrees of freedom. And we could actually see that earlier working with the table because we noticed that if we put in 2 counts, that was really enough to determine the rest of the table. You could figure out the rest just by subtraction. Okay, so this is showing the chi-squared distributions with different degrees of freedom. We're looking at the one with 2 degrees of freedom, so basically it looks kind of like this. And you notice that shape matches what we got from the simulation. So basically this is just a theoretical model for our null distribution, right? So we're using theory to tell us what values of the chi-square statistic would occur just by chance if the null hypothesis were actually true. And we can use this distribution just like we've used other theory-based distributions to find a p-value. So you're just going to shade the area to the right of your chi-square statistic. And the reason that we shade to the right is because, remember, a larger chi-squared statistic indicates stronger evidence. So we're going to find our chi-square statistic and shade everything to the right of it to find the p-value. So that area under the curve to the right of the chi-square statistic would be the p-value. In this example, it's kind of hard to see that because our chi-square statistic was so far over to the right that there's basically nothing to shade. And with a theory-based approach, this is only going to be appropriate with certain validity conditions. We're going to consider the sample size large enough here if all of the expected counts are at least 10. So you've seen this condition before. When you're dealing with binary data, sometimes you hear expected successes and expected failures instead of calling them expected counts, but really it's all the same idea.